Hello, everyone, and thank you for joining us today for our webinar on quantum computing. We're going to try and get to the bottom of this new technology and figure out the type of business value it can add to our organizations. We've got a great panel joining us today. I've got my good colleague, Jamie Soden, very good close friend of mine, who will be taking us through some of the market sizing information that he's been digging into in the quantum space. I'm also joined by the Chief Technology Officer for Atos, Sophie Proust, and Henri Calandra, expert in numerical methods and high-performance computing for geosciences. So to kick off with, I think, Jamie, you've got a bit of research that you've been digging into that you're going to set the scene with, so I'll pass over to you.
Yeah, thanks, Ollie. So quantum computing is a fascinating technology. I mean, it's really a new type of computing that provides a fundamentally new way to solve particular computations. Quantum computing creates new ways to approach algorithms and computational issues that classical computers really have quite a lot of problems with, and in particular modeling the natural world. And in his quote, Richard Feynman, one of the fathers of quantum computing, was suggesting that to satisfactorily simulate nature, you really need to use quantum mechanics rather than classical physics, because quantum mechanics are the building blocks of the atomic world. And the hope is that quantum computers can simulate the very complicated aspects of the natural world much more easily than digital computers can. So, I suppose we need to start with, what is a quantum computer, and how does it differ from a digital computer? And really, a quantum computer uses the properties of quantum mechanics to perform operations on data. And it potentially creates a completely new computing paradigm. It uses different types of hardware and different software to do calculations in frankly a fundamentally different way to traditional computers. Quantum computers run a whole new set of algorithms, which means that for some calculations it can take very powerful computational shortcuts. Quantum computers use something called qubits, which are roughly analogous to the traditional computing bit, and a qubit carries quantum information, and unlike a conventional bit in a digital computer, it can be used to show multiple states, and a quantum computer uses this property and the quantum entanglement, which is the way quantum particles interact, to store and process computations. Digital computers only have one state, whereas quantum computers have multiple states, so they can take on different different states, not just ones and zeros. Which means a quantum computer can do multiple computations simultaneously. And it's worth mentioning that a quantum computer is not fast for everything. It requires a very specific type of calculation that takes advantage of this simultaneous calculation ability. And it's really all about the algorithm. And if you compare quantum computers to digital computers, for a digital computer, harder tasks, and it's a good way of thinking about it, is that the harder tasks, they require, frankly, an exponential more resources. Whereas with a quantum computer, the more qubits you have means an exponential amount of resources that are available for a specific task. So it's almost kind of the polar opposite in some senses. So we've looked at the different types of quantum computers that are available, and if I start on the far right, this type of computer, so the full or universal quantum computer, and this type of computer is frankly the real deal, and it's where most of the benefits and a lot of the limitations lie, and they can perform the most complex of quantum algorithms. So I'm not going to go into a huge amount of detail about, what these will do. I mean, I don't, as I said at the start, the webinar is not trying to hurt you with lots of information, is it can do, you know, the most complex of algorithms like Shor's algorithm, Grove's algorithm, so very complicated quantum algorithms. And these quantum computers use quantum gates to build enough capacity to execute these complex calculations. And you know, new variants of universal quantum computers are looking to escape the current challenge, which is around you know, supercooling, and the big challenge is to get to a point where these computers can do these very complicated algorithms, you know, so the Shor's one and Grover's. And at the moment, the challenge is that, you know, they are very noisy, which means they produce a lot of errors, which would need to be corrected. And you know, and the computers themselves are a little bit unstable, so they aren't able to work for long periods of time. And so the current generation of these computers is called NISQ, or the noisy intermediate stage quantum. So we're still some way away from this point, from these types of computers, but this is kind of the, you know, the end game of quantum computing, so to speak. And if we move to the middle part, which is the quantum annealing, or kind of analog quantum computers, and this is a class of quantum computing that uses sort of analog methodologies and different quantum properties other than so different from the universal quantum computer, and it's easier to create stable, sort of more stable and workable machines using these technologies. But they have some of the similar drawbacks to standard quantum computers. So some of them require supercooling. However, the calculations that they can execute are not quite in the same class as the full quantum computer. So they can solve some of the most complex kind of classical computer computational problems. So, you know, for example, you know, a highly complex computational problem like the traveling salesperson, you know, very quickly, you know, in some cases, you know, maybe 10 to 100 times faster than a classical computer, but they're not able to make a dent into the, you know, to the full quantum algorithms like the ones we mentioned before, so Shor's and Grover's. So these analog devices will have a place in, you know, in simulating quantum environments for the foreseeable future. And, you know, companies like D-Wave Systems have demonstrated that this technology is useful in some high performance computing environments. And the next kind of type that I'm looking at is on the far left, is kind of inspired by quantum, or you know, emulated quantum, and these are frankly not at all quantum in lots of ways, but they are potentially very interesting. You know, the inspired group uses parallel processors to produce sort of quantum-like properties, generating potentially large increases in speed. The method isn't quite by brute force, but it does, because it applies the hardware to problem in a a pretty efficient way. So, for example, the digital annealer that Fujitsu has, they claim about a 10,000 time. They claim that it's about 10,000 times faster than a classical supercomputer for doing some of these complex computations. And the benefit of these computers is frankly that they exist, but they're pretty reliable, and they lack the requirement of a special environment, and you can plug these computers into your existing data center. Also, they can be programmed in a traditional manner. So the limiting factor at the moment is that they are focused, almost 100% on a particular class of computational problem, and the application of closer to real-time complex computation has a great deal of potential, and is something that kind of enables us to have a glimmer and a glimpse at what true quantum can deliver. And the uncertainty surrounding the time frame of full quantum computing provides an opportunity for some of these intermediate technologies. So, particularly as their price points will be significantly lower than the full quantum alternative for a substantial amount of time, and they will have a chance to demonstrate potential use cases for a disruptive step change in this complex computational problem solving. So, for example, closer to real-time solution for the traveling salesperson algorithm can change the way in which a transportation company implements logistics, or how a manufacturing business uses its factory resources. You know, but these computers are not universal quantum computers, and you know, and their effective use is limited to a narrow band of computational problems, as I mentioned. So, slide 6. I'm not really going to dwell on this a great deal at the moment. You know, there are probably two variants of universal quantum computers that show the most promise. You know, both of these methods have advantages and disadvantages, and breakthroughs happen, you know, all the time in this kind of technology. However, we need to focus more than just the number of qubits that these computers produce. It's really the quality of the qubits, and the noise and the error rate in which they give, and you know, how easy they are to use. So, you know, in terms of the whole or the entire quantum computer system, and this is also an important kind of factor. And so if we look at the supercomputing variant and the superconducting variant. So these are getting a lot of headlines. So this is the type that IBM and Google are using. And this represents kind of, you know, in some ways the vanguard of the technology. So these are probably the most advanced at the moment in terms of the number of qubits and what they're able to do. And this technology uses a combination of superconductors and microwaves to generate, you know, qubits at a supercool temperature. And the drawback is, frankly, this low operating temperature, you know, which creates really questions about their long-term practicality, and whether they'll be able to scale to a number of usable qubits, you know, within a, you know, reasonable time frame. Although, you know, as we've seen with some you know, Google announced only a few days ago some sort of they're making quite a lot of headway in this area. And trapped ion, as I said, I'm not going to go into a huge amount of detail. This is another promising area of research, and you know, these are perhaps less in the public eye because the research is, you know, is driven a lot more by the academic community rather than commercially. And this technology traps ions within a you know, a strong vacuum using electric field, so it doesn't use, you know, a supercooled environment. And new generations of these trapped ion machines have switched to electrical interaction with the atoms rather than lasers, and obviously that has benefits in terms of their ability to scale, but also the cost of these things, and they're more analogous to, you know, a traditional computing environment. And you know, they have the big benefit, they operate at room temperature, so scaling is simpler in the long term. But traditionally, and partly because they operate at a higher temperature, these computers have been a bit noisier. But you know, we're seeing, you know, generations of these computers coming in which have better noise characteristics. So if I look at so this slide is, excuse the eye chart, but as an analyst, you know, we get asked about the future of technology quite a lot. And I just wanted to remind people about some of the spectacular failures in predictions that we've seen in the past. And you know, I won't go into all of these different things. But my favorite is really the kind of the vacuum cleaner president that in 1955 said that, you know, nuclear powered vacuums would be a reality in 10 years time. And I tried to visualize what a nuclear Hoover would look like, but and what the purpose is. But obviously that the fact that the company went out of business in, you know, not long after that says quite a lot about that particular prediction. So I think it's important, and I think to consider, you know, some of these, and you know, the kind of, you know, the ability to predict kind of the future of technology, given how nascent quantum computing is. And I think it's important to remember that, you know, underplaying technology's impact is as prevalent in some of these predictions as overplaying it is. So, you know, when people say that, you know, there won't be a quantum computer in every home or every business, I I tend to think that that who knows, frankly, given whether that's going to happen or not, given the predictions on this list, and frankly how wrong some of the most leading minds in technology have got it in the past. So with that, let's look at the current roadmap for universal quantum computers now. So it's quite a simple chart, and at the moment I think we're at the stage of, as I mentioned before, the noisy intermediate stage quantum, or NISQ. So relatively low number of qubits, which are the building blocks of quantum, and they're relatively noisy and unstable. And I think the next, we're almost at a watershed moment at the moment. So the next 5 years, partly because there's competing technologies. So as I mentioned, the trapped ion is starting to come into being. And I think the next 5 years, we expect to see both the quality and the quantity of qubits increase, a great deal. And this means that we're able to, see quantum computers that can address increasingly sophisticated algorithms, much more quickly in many cases, but probably not enough to perform, the Shor's algorithms, and some of the that end of the quantum spectrum. And I think really we can't predict unless we see a big breakthrough in a relatively short period of time. It's unlikely that we're able to predict that this will be anything less than a decade away. But as I said, predictions are really hard to make, and breakthroughs, and unfortunately setbacks in this kind of technology can happen and are hard to predict. But I think the best minds in quantum, and I've tried to kind of talk to as many of them as I could possibly do, generally would say that the technology is 10 to 15 years away. But as I said, this could change given the vagaries of some of these things. So how will enterprises use quantum computers? And right now, I think we're at kind of this at an experimental phase. So developers are working on creating algorithms for these these NISQ variants at computers, and also the next generation where they're a little bit more stable. And we're already starting to see experimentation into the modeling of nature, and I think we'll see some examples later on from Atos and from Total as to what they're doing. And I think that's probably the most exciting part of this webinar is what they're actually doing on the ground. But we're seeing the modeling of nature through some of these computers, designing new drugs and finding new materials and new properties in materials through some of that simulation. We see some experimentation in quantum machine learning, there are some methods which will require that kind of fault tolerant end of the spectrum, but we're still seeing some solid experiments, closer to the current generation that are quite exciting. So as I said, over the next probably 3 to 5 years, we'll see quite a lot of activity in that type. And I suppose if we look at when fault tolerant, high qubit quantum computers are ready, as we mentioned before, so there's Shor's algorithm, which can help with breaking encryption, and uses this factoring algorithm if it does succeed, it will break an awful lot of the current encryption methods that are out there at the moment. And the two other kind of interesting full quantum algorithms that already exist are Grover's algorithm, which will produce a very fast method of searching unsorted data, and it will bring quantum communication, so providing very, very secure communication method into reality within that time frame. But we're still some way away. And I think we see quantum computing and quantum computing technology is looking very promising at the moment, and we see real world uses and already in existence to a certain extent, and growing within that kind of the next 3 to 5 year period. And I think at the moment, really, it's about preparation for this this event happening in the near future. And organizations that are going to invest in talent and the discovery of what quantum can do for themselves will be at the kind of the forefront of the next generation of what is a very, very big change, a disruptive change on the next generation of computing hardware and software. And there are already emulation suites out there and cloud versions of quantum available for that experimentation. So it's one of those things, is go out and explore it. At the moment, I think it's one of those things that I think a lot of organizations should at least be looking at and experimenting with. And the bottom line, so I think one of the most significant issues preventing the success of quantum computers long term is the complexity of the technology. And partly why we're doing this webinar is to I'm not sure we always succeed with because it is such a complicated area, and there's a lot of complexity in the technology. And if you require having postgraduate level atomic physics to understand something, then frankly it's a big limiting factor in any technology. So I think the core challenge, and I think something that is ongoing at the moment, is the writing of high-level programming languages that can make use of the technology and lower the barrier of that requirement as the technology moves out of the laboratory. And another challenge, and I think this was a big challenge for the early days of original computing, was abstracting the core concepts to make it easier to grasp exactly what quantum computing can achieve, and sort of democratize the technology a little bit, so that quote unquote normal people can understand and actually benefit from it. And I think it's important to say that this technology has the potential to disrupt as much as traditional digital computing did when it emerged, but probably over a shorter period of time. I think at the moment the analogy would be that we're in the 1950s, 1960s level of technology. So sort of the valve or early transistor-based kind of computing hardware, and we're sort of waiting for the integrated circuit to be developed. So that next level of hard quantum, and the programming is still in machine code, frankly, and what we need is those kind of that next level of development, so to harness quantum's full potential. But I think a lot of that work's kind of going on, and I think the good news for for quantum is that we've already been through a lot of those challenges for digital computing. So the goals and the pitfalls hopefully will be easier to manage given that experience. So at least we have been through some of that before, so we know kind of, or at least we have some of the terminology in existence. So that was kind of all I wanted to say. So Ollie, I just want to hand back to you.
Yeah, thanks Jamie. I love that slide on predictions. There's some great stuff in there. So I think what's really cool about this webinar is we've got it kind of triangulated from three people. We've got a very passionate and knowledgeable analyst. Jamie's been trying to teach me about quantum for ages now. It hasn't taken hold, unfortunately, for Jamie, but he has tried his best. But we've also got Sophie from the service provider community, and Henri from the enterprise community, that are all trying to make quantum work for their businesses and try and understand it more. So perhaps to kick us off with the next part of the webinar, if I hand over to you, Sophie, so you can talk us through what Atos is doing with quantum.
Yes, absolutely. Thank you, Holly. Absolutely. I mean, the theme of the webinar is you mustn't ignore quantum computing, and that's what we've done at Atos. Actually, since 2016, we've launched our quantum computing program. And this program is actually built around 4 pillars. The first one concerns programming and simulation environment. So we have been putting to market a quantum learning machine. I will detail it a little bit later. The second pillar is our way to contribute to the development of quantum algorithm. As Jamie said, there's a few since still, American NIST is maintaining the list of those algorithms. It's called the Quantum Zoo. You can go and Google it. And so we are contributing there too. Our third pillar targets actually the next generation architecture. So we need to think about how to build the next architecture, which will integrate those quantum accelerators. And for that, we are taking part in several European projects, Horizon 2020, for example. And our fourth pillar regards quantum safe cryptography. Because as Jamie said, some algorithm, and mostly Shor and Grover, will suddenly, when having enough qubits, enable to break RSA code. So we need to think of that. And at Atos, we are preparing hardware security modules that will embark a quantum safe algorithm when the standards will be out. And we think it's going to take some more years to come. So if we move to next slide, I wanted to give you a little bit more insight of what is our quantum learning machine. Well, actually, it embeds three main features. The first one is the programming part. We have delivered several programming languages for developers to write circuits, that is quantum programs. We also deliver libraries and some example of quantum algorithm to get you started. And a very interesting feature which is delivered is our interoperability modules. And this enables programmers to run on a QLM, so on the quantum learning machine, a program written from another environment. There's other environment, for example, Project Q or Cirque or Qiski. So you can either import a program from those environments or export them to them. So this is very interesting. And note that those connectors are open source and you can adapt them to any other environment. So the second part of our quantum learning machine, which is actually an appliance, you can see the photo of it here. The second part is optimization. And why did we deliver that? Well, because, and we have understood it through Jamie's presentation, the hardware that still into research, but there are various implementations. And they don't implement, for example, the same topology. They don't have the same possibility, entanglement possibilities. They don't react to noise the same way. This is why we have created this optimization part where we can adapt to a different kind of potential hardware. And the third part is the simulation. And this is, again, linked to quantum qubits. So we can simulate quantum qubits in an ideal way. We talk about logical qubits, but we can also bring some noise model against those ideal simulation to mimic the actual qubits. And so again, this appliance, it's a complete offering, ranging from a simulation of 30 qubits with 1.5 terabyte of memory to 41 qubits. So it's quite impressive. You can do a lot of computation there with 48 terabyte of memory. So if you switch to next slide, I wanted also to show you that with this quantum learning machine, actually you can do a lot. You can learn, and this is the benefit of it, because as we've seen, this is quite complex environment. The paradigm of programmation is completely different from a classical computer. So you need to learn how to write programs. So we have tutorials through, for example, Jupyter notebooks, but we're also able to test the programs. And this is very interesting because when you will run your program on a real hardware, you will not be able to debug. So here we will be able to give you the visibility of the transformation that is happening in every step of your program. And you will also see the impact of the hardware topology on your program. You will be able also to optimize your program using the best appropriate noise models, for example. And very important, we have the ability to run a hybrid code. We know very well today that we will not be able to run a complete program on a computing on a quantum computing on a quantum computer. Sorry, it will be more like an accelerator. So you will offload part of your program onto a quantum accelerator. So next slide, please. Actually, all this power and operational excellence and efficiency has been very well understood by our customer Total, who decided to use this quantum learning machine for his own programs and his own way to solve problems that cannot be solved yet with classical computing and improve performance and efficiency. So I propose to hand it over to you, Henry, so you can talk more about your experience.
Thank you very much, Sophie. So please, can you switch to next slide, please? Yes, for Total, high-performance computing has been for years and decades a necessary tool for helping us to solve our problem in exploration and production. However, as long as we are getting closer to exascale computers, we can see that we are moving to more and more complex classical HPC system, and there are several reasons for that. We can see that we have fundamental limits on the transistor scaling, on the energy consumption. Clearly, for years, we are reaching some limits in the frequency range of the processor. We see an increase of the component inside the technology. And also, what we can see that HPC systems are becoming much more heterogeneous and massively parallel, and integrating more and more complex technology, hybrid technology. So most powerful computers we use today are accelerator-based computers, and we have no choice but using these computers. And this has some problem in the programming model, in the looking to the parallelism of the application. We are still limited by the well-known Adam's law. We have to look at all the algorithmic parts of our application. And another reason also is it is said that Moore's law will end by around 2025. Then all these reasons show that we are moving to more complex system. And next slide, please. We still have compute requirement which continue to grow. For example, in seismic depth imaging, we want always in our business to compute better and faster, to integrate more physics, more data, more integration of multidisciplinary problems to help us to solve a new problem. We have to introduce uncertainty quantification. We would like to move to some more real-time-like simulation, where, for example, as I show here, we could drill and image at the same time and improve the imaging during the drill, which will reduce the cost. In a reservoir simulation, it's the same problem. We have more and more complex field. We have more different fields, different physics to be integrated. We have very strong geological heterogeneity, and we need massive simulation to be able to produce accurate results and to predict oil production. Next slide, please. But it's not the same. We want to do more. We want to do more. For example, we are getting more and more data from different sources, from many sensors, from fields, from satellite. And we would like to integrate all this data all together to get the value of this data and providing us a correct tool for our business. And there are a lot of range of applications we would like to develop, taking advantage of this huge amount of data. But also, optimization problem is becoming a very important problem in our business, not only for managing the large gas field or the cluster of reservoir and producing the oil and gas production, but also for refinery, for example, refinery blending, to schedule our production, shipping, and all these are based on linear programming model, which are very difficult. We call it combinatorial optimization problem, and they still require a lot of computing resource, computational material science also, including quantum chemistry and material science. These are very important and more needs for us to solve such problem. For example, for catalysis, solvent, lubricant, batteries, then you can see that we are more application coming and more we want to do. Next slide, please. In fact, what our goal is always to compute better, faster, to solve some problems which are intractable today on classical high-performance computing. And this is a reason why we need to explore disruptive technology, alternative technology, and this is why we are exploring quantum computing as a disruptive technology and trying to see how this new technology could be helpful to solve part of our needs or some of our problems. For that, we have identified a roadmap of use cases. Next slide, please. And depending the evolution of the technology, it has been very well explained before. We have today access to the NISC device with a few amount of qubits, less than 100. And we're expecting more and more qubit and stable qubit, less noisy technology. Then for that, we have several potential use cases we have identified, such as quantum chemistry. We believe that we might be able to, within 3 to 5 years, to have some relevant use case showing the advantage of quantum computing on this topic, and then quantum combinatorial optimization, which requires maybe a little bit more a stable device with more qubits and more stable qubits. Then quantum machine learning will come after that, even if at the same time we can see that we have to explore this algorithm and this technology. And very long time when we hope having access to error-corrected quantum device, we will be able to address scientific computation on this quantum computing device, revisiting our algorithm and adapting our algorithms to take advantage of the huge power computing we can get from this technology. Next slide, please. So what have we done so far? We need to understand how to program this technology. And for that, we decided to start a project a year and a half ago, almost 2 years ago. And first of all, we decided to acquire the Atos QLM device to help us to develop, to understand the algorithmic part, to understand how to develop quantum algorithms and what are the quantum algorithms we could develop first. And we decided first to develop what we call quantum variational algorithms, which are well designed for NISC technology. We can today apply to some simple problem in quantum chemistry using the variational quantum eigensolver, VQE, or in optimization problem using the quantum approximation optimization algorithm. And we have done some developed this algorithm in-house to understand exactly what is the meaning of developing quantum algorithms, how we can use it, and what are the implications in terms of redesigning algorithms, understanding the physics, and how to formulate our algorithms. And so the beauty of this platform is that we can develop algorithms easily. We can test it at quite large scale. We have up to 35 qubits. And we can also port and simulate at least the behavior of the algorithms on actual computers. Then this is what we call hybrid quantum computing, and this is today one of the only way to address this problem. So last slide, please. I will show you some results we obtained on quantum chemistry with using VQE. We have tested this in-house algorithms we developed last year, and we have tested it to a large amount of molecules to see the validity of our algorithms. And you can see that we are moving to more and more complex molecules, and now the goal is to continue to explore this technology and to see how we can, working with our colleagues in a different domain, can move to more complex problem, defining use case, and how we will be able to acquire the necessary experience on this fantastic technology. So I'm done on what I wanted to say. Thank you.
Perfect. Thank you ever so much. There's a huge amount of information coming around here. I mean, this is just a reminder to everyone listening in, do please ask questions as we go along. We've got some really good questions coming in already, inspired by some of the insights that our three panelists have given to us. I'll kick off with the first one. I think this is probably, well, it's your slide, Jamie, so I think we'll point this one towards you to start off with, but everyone else do feel free to join in. And I think this is based off a couple of really exciting announcements that have happened recently in the space. So relative to slide 8, how does the recent quantum supremacy announcement, which happened on September the 20th, 2019 on NASA's website, relate to Google's first calculation on a 53 qubit quantum computer?
Yeah. Ollie, yeah.
I'm hoping you've got.
Yes.
You've
no,
got the
I
handle
do.
there.
Yeah, no, I do. So it's an interesting question. I think it's one of those things, and it's something I have had a look at, and I think looking at and I have to trust the judgment of some of the academics that have kind of weighed in on this, and I think so there have been some questions about kind of the experiment itself, but if we put that to one side, I think this is a milestone, frankly, in potentially in the quantum world. I mean, it certainly moves things forward, but I'm not sure the claim has been 100% proven. And what we're talking about here is something that is, at least in my understanding, is not necessarily a practical use of quantum computers. So I don't think it really affects the overall time frame, particularly. And there have already been, I suppose, sort of quantum computers that have got more qubits than that. So I think again, it's exciting, and but it's still a somewhat away, and it's another kind of step. But I don't think it really changes. It's not a step change in terms of fundamentally a whole new level of the number of qubits that are there. I don't think it's a step change in the algorithm that they're using, but it is another kind of example of how quantum is being used, and that's obviously exciting. And the claim about supremacy, I think we've still some way away from deciding whether that's absolutely true or not. But yeah, it's really exciting.
But I mean, you mentioned a word there that I think is really interesting, which is practical. And we've got another top level question here, quite a high one. And it might see your name feature on one of those slides of yours. But if you could put your predictions hat on, when do you think practical quantum computing will exist?
Yeah. I think so. I think practical is a kind of an interesting word here, and I think, you know, so the work being done, you know, at the moment, although, you know, not practical, doesn't necessarily make you know, a real quantum computer more likely. It helps further our understanding of quantum itself. So the fact that a lot of the work at the moment is kind of experimentation, it sort of means that we're getting, you know, so that experimentation, and I think, you know, the Google kind of example says that it helps us to further, you know, to a certain extent, the quantum computing itself and get further in that goal. So in that sense, it's good. But also any experimentation around quantum computers kind of impacts, you know, our understanding of quantum computing, of the quantum mechanics, and so that furthers our scientific example. So I think that's always good. But I don't think, and I think I stick to, you know, my kind of guns really. And I think, you know, for full fault tolerant quantum, you know, that can handle some of those big classical algorithms, you know, very, very quickly. You know, I think we're still kind of that decade away. I don't think that.
Okay, fair enough. And Sophie, if I was to force you to put your prediction hat on, when do you think we'll start seeing some practical quantum computing solutions out there?
Well, you know, I think things are moving. As we said, we think in a few years we will have some NISC and some possibilities to run some programs there. What we're working on is to say, since we will have not such big numbers of qubits available, we really need to work on the algorithm, on the way to downgrade perhaps a problem, to find where the quantum advantage, as we said, will be the most efficient in the part of the algorithm we are going to design. So we need to figure out which feature, which function we can upload to this NISC, future NISC coming along in a few years now. And really benefit from the quantum acceleration. Those algorithms must be also, you know, resistant to noise. So we really think of this hybrid way of programming, and also the need to work in an iterative way. What we are proposing, for example, with the quantum learning machine, is to execute your circuit and then in an iterative way handle adapt your program to the response of the noise that you will have on your hardware. So you can arrive to something very, very efficient for a specific feature function in your overall algorithm.
Okay, that's really interesting. And Henry, I suspect you can see where this is coming. It's your turn with the crystal ball. When do you think we'll see practical quantum computing solutions?
It's difficult to say, but what we can say today is that we know how to implement some algorithm. Maybe, let's say, coming back to the quantum chemistry. We know how to, what is difficult with quantum computing today is the state preparation. How do we prepare the data? It's a very huge problem and very costly problem. We cannot run any data or any amount of data on quantum computing. It costs a lot. But if we look at quantum chemistry, we have tools to formulate, to define the Hamiltonian of molecules, to explain it in terms of gates, understandable by quantum computers, and we can start running these variational algorithms, which are hybrid algorithms, which are algorithms taking advantage of the quantum computer to compute the objective function we want to minimize, and we use the classical computer to optimize and to define the next, to optimize the parameters. And with that, we know that we are able to implement algorithms and test it on some molecules. Today, a CO2 requires 24 qubits. If we want to move more, For example, to sulfur, iron sulfur, we need more than 100 qubits. Meaning that if within the 3 to 5 years, we can have access to more than 100 qubit system, we will be already able to implement quite large molecules which are of interest for our colleagues and start introducing some workflow. But still, we have a lot of research, algorithmic research to achieve, because all these algorithms we are developing, VQE or QoA, we know that they are working on a limited number of qubits. How will they behave when we will use a large number of qubits? Are they scalable? If we come back to classical HPC terms, will they scale? So we have this important research to be done. On quantum machine learning, it's the same. We can maybe work on the hybrid approach where we can take advantage of the quantum computing to reinforce the machine learning, and again, on the classical side, to perform some optimization. What we have seen also is that optimization on the classical side is quite very important, and and results might differ a lot depending what optimizer you are using on the classical side. So you see, we still have a lot of research, algorithmic research to be done on both sides. For the other algorithms, solving PDEs, partial differential equation, it's another problem. One first limitation is everything might be fine as long as you stay in the quantum world, but as soon as you measure, you collapse everything. So you will get only one point. So what is the meaning of solving a PDE's partial differential equation, or ODEs, or ordinary differential equation on a quantum computer if you cannot get a solution? Then we have to see how we can integrate this in a larger problem, and certainly optimization problem will be the solution. It's a long way. It's a disruptive technology. We have to learn a lot on both sides, on how understanding the technology and how we have to develop algorithms. But I really don't know what is the future, but we are trying to take advantage of it. And one most important thing is understanding how to develop the algorithm. I think this is the biggest shift and disruptive things we have seen this last year in our scientific world.
Cool. Okay. I mean, sticking with you, Henri, because we've got a couple of questions here that are really kind of interested in the type of ROI you got from some of those use cases that you described in your slide deck. So, I mean, start off with one element of that. How do you calculate ROI in that space, and what sort of ROI have you seen?
Well, this is a very good question, and honestly, we are still at the beginning of this research, and we don't know yet how to answer that. What we know is there are some use case we cannot run on our computer, on in-house computer, because the formulation is the way it is. We cannot take advantage of the high-performance computing, the classical way. And we think and we see some possibilities using this new technology. Then, if we succeed, then we will have use case we can run, or we can get results we could not have without this technology. Then this will be a huge progress, because we will be able to integrate that in our process. So this is my only answer on that.
Fair enough. Thank you. I'm just conscious of how much time we have left, and I think given the nature of some of the questions that have come through, I think the best way of answering as many of those as possible is if I give each of you 60 seconds to describe the things that people need to go away and do or think about right now. So perhaps starting with you, Jamie, what 2 or 3 things should people go away and think about doing right now? It looks like we've got an audience full of very engaged people who are passionate about quantum and the potential it can bring.
Yeah, I mean, it's a good question. I think at the moment we're still very much in the experimental phase, and so the most important thing to do is, frankly, experiment. So this means a number of things, but it's looking at kind of having the right talent in place to explore quantum. For some technologies, and some of the use cases. So for example, if you're in manufacturing, it's it's important to kind of have a think about what it could potentially do for you. So we've seen so the high performance computing and sort of the inspired by quantum computers kind of having a big impact in factories to do with something like robot arm movement, so optimizing the robot arms by using high performance computing or real-time algorithms to do that work. But also if you're in logistics, so it's looking at fleet movement optimization for lorries, but really any kind of so if you're in an industry that has any type of scheduling, there's a complicated set of interwoven tasks. So for airlines, timetabling or sort of other things, is that so it's thinking about things where having that kind of real-time optimization, once it becomes possible, what are the kind of the advantages of doing those sort of things. So anywhere where you have a complicated system where potentially there's an algorithm that can be done either at the moment, if it's done in a batched style way, if it's something that potentially it could be done, you think about the possibilities of doing it in real time and how that can potentially change that or disrupt that market. So we've seen modeling of complex systems like equity trading, and people thinking about algorithms for doing that. So essentially modeling the system and using quantum machine learning to make better market predictions. So there's all sorts of things like that. So really it's about thinking about the applications of quantum. I've probably used more than 60 seconds. Apologies. You did
slightly, but we'll let it slide.
I tried to talk fast, but it didn't work, did it? Sorry.
Sophie, same question.
Yes, okay. So perhaps to be really quick, I think on the hardware side, we can do some active watch, go and see the technologies around, what kind of issues are they having, and try to understand better. But then it's true that the best way to go for quantum computing is looking at the software, and we have to go very much ahead, because it's difficult to understand. We've talked about it. Where the features, where are we going to be able to get advantage of this quantum speed up? We are looking, for example, for algorithm on unsupervised machine learning. There's going to be a lot of interesting things around. So yes, I think going for the software is the best thing we can do for the time being.
Wonderful, thank you. And Henri, finish us off with some sage wisdom.
What is important is, first of all, is to identify use case and application we could use, and what are the algorithms. Understand these algorithms, understand the hardware, work with the vendors and all the people and research labs developing that to understand the technology. Software is very important to understand how to develop these algorithms and to get a good software. Portability will be important. We see many different systems would like as a user and users to get only to reduce the number of platforms. It will be very useful. Identify the good network, academic and industrial partner network is also important. And I think what's the most important is to educate, train young research generation who will be ready when this technology will become reality.
Wonderful, thank you. So there's plenty for everyone to work on and keep themselves busy with. So we're completely out of time now. So I just want to say a big thank you to our panelists. Thank you so much for joining us and sharing your story. And of course, a big thank you to everyone who attended today and asked those questions. Do keep following HFS for some more coverage on quantum and some more news on quantum. It's a very exciting area. So thanks a lot, everyone.
Thank you.
Thank you.
Thank you.